Alright guys, this is the first video for the AP review session. First of all, when you're working your FRQs, make sure you show all your work. Start by writing out the formula that you're going to be using to solve the problem. Next, solve the formula for the variable that you're asked to find. Finally, substitute in your numbers. Make sure you include the units. At the end, obviously calculate your answer. Be sure to include the units on your final answer, and make sure you round to the proper number of significant digits. Don't leave your answer with more significant digits than the original problem
Come to the main office, Chad Taylor.
gave you to start with. If an FRQ asks you to justify your answer or to explain, make sure you use complete sentences. Make sure you write very clearly, very neatly. Over-explain things. Remember that the reader's opinion of you is that you probably don't know what you're talking about, so you need to prove that you do. Make sure that you address all the verbs in the question, address those completely, leave no doubt that you know the right answer. If you do use a formula or a diagram, make sure that you explain it in words. The diagram especially cannot stand alone. You're probably going to be asked to draw free body diagrams. Make sure that those free body diagrams only include real applied forces. They should not include net forces. They also shouldn't include components of forces. For example, if you were drawing a free body diagram for a pendulum type problem, and this was equilibrium, and then you displace the pendulum to this point at a certain angle. Normally, if we were working the problem, we would need to draw in the weight, and we would need to break that weight into components, like so. Where this is the weight, this is the parallel or the restoring force, and then this force right here is going to give us the tension in the rope. That's not a free body diagram. If you were drawing a free body diagram for this pendulum bob, you were drawing the pendulum bob, you were drawing the weight straight down, and the only other real force acting on it is the tension in the rope, which is acting like so. So that would be your free body diagram. If you were doing a free body diagram for like an Atwood type machine problem, and you had two boxes arranged like so, and you wanted, and let's say there's no friction. You want to draw a free body diagram for that particular box. You would pull it out, draw all the forces acting on it, which in this case would be mg, weight, acting down, normal force, acting equal but opposite. Those two arrows need to be the same length because the forces cancel out. That's not G, that's the normal force. And you also have that force, which represents the tension in the rope. So the tension in the rope is the net force acting on that box. If you were drawing a free body diagram for this box, mg down, we know it's going to accelerate down, so that force, mg, is bigger, so the arrow must be longer than the other force, which is tension acting up. One more example. If you had a box on an incline, like so, and you knew that this angle was like 70 degrees, had your box up here, and you were trying to find the acceleration or something like that of the box. Normally, you would draw in the weight, you would break that weight into components. One component parallel, one component perpendicular to the surface. This angle is the same as that angle. That's not a free body diagram. Let's say this box had friction acting on it. So what you would do, go ahead and draw your inclined plane, draw your box on the plane, but in terms of your free body diagram, the real applied forces to this box are mg down. You've got a normal force, the surface is pushing up on the box and it's pushing perpendicular to the surface, so that's in. And if there's friction, you would also have a force pushing that way, which we'll label FF. So again, free body diagrams show only real applied forces, not components, not net forces. All right, also check your calculators before you go in and take your test. Make sure that they have good fresh batteries, and make sure that your calculator is in degree mode. You calculus students especially, make sure you're not in radian mode, make sure you're in degree mode. So let's work a couple problems. First one, friction provides the force needed for a car to travel around a flat circular track. What's the maximum speed at which a car can safely travel if the radius of the track is 90 meters and the coefficient of friction is 0.5? You got to remember on a problem like this that the friction force is acting as the centripetal force. So you have to say FC equals FF, like so. You want to show all your steps. So you know that FC is mv squared over r, and that friction is mu times n. This specifically tells us that this is taking place on flat ground, which means the normal force is equal to mg. Your masses cancel. We solve that equation out for v. We would get v equals the square root of r u g. And then we would plug each other from that point. And remember that when you're doing this, you want to plug in your numbers so that they see what you're doing. You want to show all your work. So we have a radius of 90 meters, the coefficient of friction of 0.5, and g. So multiply it out. 90 times 0.5 times 9.8. Take the square root. We get 21. And since this number right here has 2 sig figs, we don't want to have any more than that. So 21 meters per second. That's what we're looking for on number 1. Problem 2. Problem 2. A 2.5 kilogram bucket on the end of a 1.8 meter string is swung in a vertical circle 4 times in 2 seconds. What is the period? So this thing goes around 4 times in 2 seconds, which tells me it goes around 2 times per second. That is a frequency. How many times per second? So that's our answer to number 3. Frequency is 2. If the frequency is 2, the period is 1 over frequency. So the period here is 1/2 seconds, 0.5 seconds. To find the linear velocity, the easiest way to do that is to use v equals 2 pi r over t. All right, so because remember that 2 pi r is the circumference, period is the time it takes to do that. So 2 pi times the radius, which in this problem the radius is the length of the string, 1.8 meters, all over the period, which we just calculated to be 1/2 second. So 1.8 times pi times 2 divided by 0.5. So we get a linear velocity of about 22.6. And actually, yeah, with 3 sig figs, 22.6 meters per second. Centripetal force, again we know, is Fc equals mv squared over r. So the mass of our bucket is 2.5 kilograms. Velocity, it's the linear velocity, 22.6 meters per second. You got to square that. And we want to divide that by r, which again, length of our string is 1.8 meters. So if we do the math, I'm getting about 709 for the centripetal force. 709. That's newtons. All right, to calculate the tension at the top. All right, I want the tension up there at the top. Think about a free body diagram. Up here at the top, you have mg pulling in. You also have, on top of that, tension pulling in. So up at the top, the centripetal force, Fc, is equal to tension plus mg, which means that tension equals, if we solve that out, Fc minus mg. We already calculated the centripetal force is 709. And mg is just the weight of our bucket, which is 2.5 times 9.8. So that's 24.5. Subtract that out. We get a tension of 685 newtons. So that's at the top. Now at the bottom, let me make some space here. Let's draw a free body diagram for the bottom. At the bottom, we have mg acting downward, but we have tension, bigger force acting upward. We know this thing's going to accelerate toward the center. It's moving in a circle. The centripetal force, when things are moving in a circle, is the net force. So that force is T minus mg, which means T equals Fc plus mg. Again, the centripetal force was 709, and the weight, 24.5. We add those up, 709 plus 24.5. We end up with a tension at the bottom of 734 newtons. That's that set. So if we move on to the next slide. Give me just a second to get this straight. All right, so let's try this again. So this time we've got a satellite, and that satellite is orbiting the Earth. We know the distance it orbits the Earth, and it's keeping a constant distance, so it's a circular orbit. We want to know the satellite's orbital velocity. When satellites go in orbit, what's keeping them in the orbit is gravity. And the gravitation force is acting as a net centripetal force. So set these two equations equal. We know this is G, M1, M2 over R squared. And we know centripetal force is V squared over R, mv squared over R. The masses that cancel here are the masses of the satellite. So if we solve this out for velocity, we need to multiply, this is R squared here by the way, multiply both sides by R. We end up, when we do this solving out, of V equals the square root of G, mass in this case of the Earth, over radius. So we plug and chug. V equals 6.67 times 10 to the minus 11, that's the big G, times the mass of the Earth, the mass of the central object, which is 5.97 times 10 to the 24 kilograms, divided by the radius, the distance between centers, 8 times 10 to the 7th meters. We'll take the square root. So when we do the math on this, it might take a second. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 divided by 8 times 10 to the 7. Take the square root. We get about 2,231 meters per second. Be careful though. We only got 3 sig figs in the problem. So we probably should round it to 2,230 meters per second. Next part asks us to find the period. The easiest way to do that, if we already have the velocity, is go back to this equation we used a second ago. That's the velocity for things moving in a circular path. Solve that out for period. So period would equal 2 pi r over velocity. So in this problem, 2 pi, radius, 8 times 10 to the 7th, divided by the velocity, which we just calculated to be 2,231 meters per second. So do the math on that. 8 times 10 to the 7th times pi times 2 divided by 2,231. When we do the math there with the 3 sig figs, 2.25 times 10 to the 5th, and that's seconds. That's our period for that satellite around Earth. One more on this slide, seesaw problem. All right, so this one says we have a seesaw. On one end, we hang a 6-kilogram box. The seesaw is made out of a 2.4 meter long board. That's from end to end. It's a uniform board, and it has a mass of 24 kilograms. So in a problem like this, we want to think about the center of mass, center of gravity. Right in the center, 1.2 meters from each side. And we want to think of all the weight of that acting at that point. Again, this is a 24 kilogram board. We know for this thing to be balanced, the torque on the left has to equal the torque on the right. The torque on the left is going to cause this thing to move in a counterclockwise way. So that's going to create a positive torque. Torque on the right is going to cause the seesaw to move in a counterclockwise way. Said that backwards. In a clockwise way, that's going to be a negative torque. We know torque is force times distance times the sine of the angle it's applied at. These are applied at 90 degrees, so that doesn't matter. Same over here. So we're going to call the distance between, we're trying to figure out where our pivot point goes. Our pivot point needs to go somewhere close to the 6-kilogram box. So we're going to call the distance from the end to the pivot point x. And if that's true, the distance from the pivot point to the center of mass is 1.2 minus x. So over on the left, the torque would be 6 kilograms times 9.8, because this is about force, times distance, x. That's equal to the force on the right, which would be 24 kilograms times 9.8 times 1.2 minus x. It's 1.2 meters. So we can cancel out the 9.8s. So that gives us 6 kilograms times x equals. We're going to distribute that 24. So we're going to say 24 kilograms times 1.2 meters. That's going to give us 28.8 kilograms meters minus 24 kilograms times x. So all we did is distribute over here. We're going to add the 24 kilogram x to both sides. That'll give us 30 kilograms times x equals 28.8 kilograms times meters. Divide by 30 kilograms on both sides. When we do that, x equals 0.96 meters. Now that's not the answer. That's the distance from the 6-kilogram mass to the pivot point. We want to know the distance from the pivot point to the center of mass, which is 1.2 minus x. So 1.2 minus 0.96, that distance is 0.24 meters. And that's our answer to problem number 11. All right, one more problem here to go. If the Ferris wheel has a radius of 8 meters and rotates with a tangential velocity of 8 meters per second, what's the apparent weight of a 60-kilogram rider when the rider is located at the top of the wheel's rotation? So draw a picture. We got a radius of 8. Don't mistake that for a rope or something. Not a rope, just right into the radius. The rider is sitting up here up top on a seat. The Ferris wheel is rotating with a tangential velocity of 6 meters per second. The guy's mass is 60 kilograms. First thing we need to do is a free body diagram for the guy. So while he's sitting up there, his weight is acting down, mg. The seat is applying a normal force to him, up. mg is bigger than normal force. So we're going to write the centripetal force, the net force acting on him, is equal to mg minus n. Solve that for n. N is going to equal mg minus c. The apparent weight is normal force, the force you feel. We can rewrite that as n equals mg minus mv squared over r. So mg is going to be 60 times 9.8. His weight, his real weight, that's 588. And I'm going to just do mv squared r on my calculator. You should show this on the test, but v squared, v 6 squared, 36, times mass. Mass was 60, divided by r, which was 8. So mv squared r is 270. We subtract those two. So up at the top, the apparent weight, or the normal force of the guy, is 318 newtons. And then finishing it up, we're doing down at the bottom. Down at the bottom, mg is acting downward, but the normal force is acting up. Here the normal force is bigger, because we know he's accelerating toward the center. He's in uniform circular motion. So we're going to write Fc equals normal force minus mg. Would therefore, n would equal Fc plus mg. And like we saw a second ago, the centripetal force was 270. The weight of the guy, the real weight, 588. So we add them in this context. And when we add them, we get an apparent weight of 858 newtons down at the bottom of the rotation. Hope that helps.